Seria diferente, por exemplo.
Tá ao vivo, né?
Então, por exemplo...
É porque faz essas palavras.
Porque também agora fala fenomenologia.
Acho que começou aqui. Começou. Começou. So, today we are gonna have a new addition to our team, our new postdoc, Gabriela Lichtenstein. I speak correctly?
I don't know. I don't speak German.
So she's gonna talk a little about herself and her research, and some of perspectives of what she is going to do here in our group, our astroparticle group in IIP. So let me just put here a presentation. Okay, the stage is yours. Yeah.
Thank you very much. Hi, everyone. Today I'm going to talk about the last two papers.
Sorry, I think that in the Google Meet they are muted.
I'm okay. Apparently I'm muted. So wait.
Just check, please.
Here?
No, Google Meet. The second is green.
Oh, okay. This one? Can everyone hear me on Google?
Yes.
Okay, good. Where's the presentation now? Oh, okay, good. So I'm starting again. Hi, everyone. I'm a postdoc here at IIP, and I'm going to talk to you today about the last two papers I wrote in collaboration with the Australian professors I was working with, Michael Schmidt, Herman Valencia, and Raymond Volkas. We did a study of charged lepton flavor violation in the triality models. And, well, the first part, I'm going to talk to you about the phenomenology on µTRISTAN. This is a proposal of a new collider. And the second part, I'm also going to talk about the one-loop corrections. Oh. This one?
Yeah.
Okay. So just to let you know who I am and present a little, because I'm new to the group. Okay, just 1 second. Deu certo? Agora foi? Okay. So back to the slides. I just want to introduce myself quickly. So you can call me Gabi or Gabi. And I did my master's and PhD at USP in São Paulo, where I did mostly studies of LHC phenomenology. During that time, I also spent 6 months in Fermilab. However, when I got to Fermilab, my host was more interested in dark matter and different kinds of searching for new physics. So we spent that time discussing dark matter in direct detection and a little bit of neutron stars. I learned a lot about those things, but they were very new to me. I finished my PhD, unfortunately, on the first week of the pandemic lockdown. And I already had a postdoc in Australia to go to. However, Australia was extremely strict during the pandemic, and I could only go 2 years later. So I have a big gap there. And in the end of this pandemic time, I got the 6 months fellowship to work at Unicamp, where I joined the collaboration LARIAT. This is the Fermilab collaboration. They made a kind of a test for Dune. And in this work, we do some data analysis of kaon and argon cross-section. Later, I finally got to go to Australia for 1 year and a half in a postdoc at UNSW, where I did the flavor pheno in the work I'm going to present today. And now I finally got here to IIP. I'm not exactly sure what I'm going to do, probably more collider phenomenology, but I'm also open to discuss dark matter and things you might think interesting. Yeah, and the pictures there. So there's the picture with the baby calling in Australia that was extremely cute. And the second picture is actually the other time I came to IIP. It was Darkwing 2019. And these are some fellows, some friends I made in Fermilab. They're all Brazilian researchers. And funny thing is that the first one is Ernesto. He was my supervisor at Unicamp later on. So, okay, so I think you're all familiar with the standard model, right? Can I go from there? And I do mostly beyond standard model physics. And in particular, today I'm going to talk about flavor physics. So flavor physics, it's actually not one question, but many questions we can make about the standard model. First, we can think about why there are 3 families. If there's a 4th family, for example. We also want to explain the mixing pattern. So we have the quark mixing pattern very well explained. The lepton sector, we can do, there are a lot of new models trying to do symmetry that would explain, or maybe that would explain it all. Another question is to include the neutrino masses. And finally, we have the charge lepton flavor violation. That is the topic I'm going to talk about now. So the standard model, we have the mixing pattern with the quarks. Are you familiar with that, with the CKN? Yeah, there are a few younger people in the back. It's okay? Yeah. No?
We haven't taken
Any course? Okay, so when we describe the masses of the quarks, do you know a little quantum mechanics? Okay, so you have the eigenstates of mass and the eigenstates of interaction of the quarks, but they are not the same. You have a rotation in between them. So if you diagonalize the masses, the interactions are not diagonal. So you can have interaction between different flavors of quarks. You can have, you see that you have up, charm, down, strange, and bottom. So each column is one flavor. In the quarks, you can mix them, but not in the leptons, okay? However, if we include masses for the neutrinos, you need to have this mixing also. So we have observed a neutrino oscillation. So you have, for instance, you have the sun, you expect a certain amount of neutrinos from electrons and mu's and taus to arrive in the Earth. But what we observe experimentally is a different proportion. So that means that the neutrino mix while coming here. This oscillation shows us that neutrinos can have masses, because the way we know how to describe the masses is similar to the quark sector. So we need to change this mass and interaction eigenstates so we can describe them both. If you do that to the neutrinos, you have a completely different mixing pattern, and you can have flavor violation, because we think that the leptonic sector, they don't have flavor, right? They don't mix the flavors. We never observed that. But if you include that to the neutrinos, there's no reason why you cannot include that to the leptons. However, we never observed charged lepton flavor violation. That means some electron interaction, and in the end, you have muons. We don't observe that experimentally. So,
Javi,
yes.
I have a question, but this interfere with the hierarchy problem, I think, or it related with. Because, for example, you are not violating the energy. If you try to produce, okay, depends. I think depends on the momentum of the electron, for example. But in order to produce a tau,
No, you said the hierarchy problem. Is that's your question?
the hierarchy of masses.
Oh, the mass hierarchy. Yes. Yeah. No, that interferes with the mass hierarchy. Yes. So you can have a flavor symmetry that is beyond standard model that would explain the mixing or the mass hierarchy. Yeah, that can happen.
But there is a kind of theory or something, because, for example, I saw a hierarchy that is muon, electron, and tau. I think these 2, 1, 3, I think. There is a kind of combination that allow us to have that flavor violation, lepton flavor violation, in order to produce the other particles heavier than the other ones. I'm asking because I don't know anything about it. I didn't study this, but I'm curious.
So you have two different, the thing is, you can ask yourself two different questions, okay? One is the interaction mixing pattern. If you can observe, for instance, you have here a muon going to an electron and a gamma and a photon. So can you observe that? That's one question. And the mass hierarchy, that's another question. There are theories that want to address both. There are theories that want to address one of them. So today I'm going to talk only the interaction part, not the mass hierarchy mass. I've worked before with theories that would explain the hierarchy mass and not the mixing. So each BSM theory can do something. It can explain, some can explain both, some would explain one of the two questions, okay?
So we just need to treat the both questions in different ways. No, it is not, they are not related between them.
Well, it depends how you build your model.
Okay. So in this case, we are just talking about electron flavor violation, and that's all. We are not worried about the mass.
Not in this case, no. But
okay.
It is a problem, and you could maybe think about or extend your model to address both questions. But today I just want to focus on the charged lepton flavor violation. Okay.
Okay. Thank you. Sorry.
Okay, that's okay. So I'll go back from the second part of the slide. So the experimental bounds, they are very stringent. We have experiments that are focused on mu decays and mu interaction with nuclei that would see this muon to electron, I forgot the word, this muon and electron interaction, okay? The conversion. However, we don't have that much information experimentally about the taus because it's harder to measure, okay? The taus have a shorter lifetime, it's much harder to see that, okay? So this is where we introduce the model. The model is called lepton triality. This is motivated by flavor structure models with an A4 discrete symmetry. So these were models that were proposed to explain these mixing patterns of the fermions, okay? So we don't address the mass problem as it was Lucia that asked, right? So we don't introduce the mass hierarchy. We just want to show you this interaction pattern, and I'm going to focus here in the charged lepton sector. However, if you have a full A4 discrete symmetry, there are some other papers that would show you how to obtain the quark sector, and you could also include the neutrino masses. That's another possibility. Okay, let me go back to the model. So this lepton triality, it would have remaining Z3 flavor symmetry. So this symmetry would let us the leptons transform as this omega with a charge T. Omega is this exponential of 2 pi I over 3. And T is a charge that can vary between 1, 2, and 3. It's a triality charge. And the same thing for the left and right hand. The Higgs quarks would be singlets under triality, and the Yukawa Lagrangian is diagonal under Z3 also. So the interesting part is that those charges, we're going to charge the 3 leptons with this triality charge. So the electron would have T equals 1, muon 2, and tau 3. And the structure we inherit from the model allows only interactions that sums to modulo 3. That means that if we have a mu to E gamma, mu is 2, E is 1, T is 1, so the difference between them is only 1. And this is not allowed in our model. So it explains the experimental bounds. But it does allow us to have a preferentially of a third family interaction. So you can have tau decays. Since tau is T equals 3, then you have mu plus E minus, and this is T equals minus 2, 1, and 1. So this size is 0, and this size is 3. And this is allowed in this symmetry. Okay? Is it strange? It's a little strange. So that gives us 3 possible models of interactions with a doubly charged scalar that is a new scalar. Okay? So
Could you go back again and explain, because I think I'm missing something like this. What's the difference?
but
So, can you explain again this relation between the muon decaying to the electron and photon?
okay, so this Z3 flavor symmetry, it will be, sorry, I'm going to write on the board, it's hard. So it will be a 3 by 3 matrix with this omega E to pi I over 3 and some charge here.
Okay.
So we have a diagonal with the 3 charges.
Mhm.
Okay, that means that since we're only charging the leptons, the charged leptons, and they're going to transform with this triality charge. So we can address the triality charge 1, 2, and 3 for each lepton.
Mhm.
And this I don't have details, but the structure of the symmetry can only allow processes that has this triality charge equals 3.
Okay. So this is like a selection rule for this charge.
Yeah, I mean, you have charge conservation if you have electric charge. And this
Like
symmetry
the
would
charge of
impose
the-
a triality charge that you need to conserve T equals 3.
Okay.
So you can allow the first can allow the second decay, but not the first.
Okay, so the entire process, including the initial and the final state.
Yeah, it's the difference between the initial and final.
Difference.
So can you explain why the difference must be 3? Because if you analyze like the electric charge, they should be equal. The final state is there.
Yeah, I don't remember by heart, but it's something with the Z3 symmetry. You have the A4 symmetry, then it's broken into this Z3 flavor symmetry. And I don't remember now exactly why it sums to 3. I can check it and then come back to you later. I'm not sure.
This A4, for example, is called modular symmetries.
Yeah.
And there are a lot of people that work on this kind of symmetries to explain flavor violation, etc. But then in this case, you have, so in this case, it's not the difference. It would be the sum of the charge in the initial and the final state. In the final state should be 3 because we have 2 plus 1, 3. And then 3 plus 0.
No, but it's final and initial, so it's 1 the difference.
Because in the final state of the second diagram,
The
you
first
have
one
minus
not
2 plus 1.
No, the first one's not
Yeah,
allowed.
the first
Okay,
one's not
yeah.
allowed.
There's a big X. Like
Exactly. The first one is not allowed because if it was, we would have very stringent
Okay.
bounds with the experiment.
So the difference is 3.
Yes, exactly.
Yeah.
Okay.
We have 3 one side, 0 the other. So this is allowed.
I got it. Thank you.
It's the difference.
Yes.
Okay.
Okay.
Why it's exactly 3? I don't remember now. It's something with the symmetry. I'll go back to you later. Okay, so so we would have this K that is our doubly charged singlet. It could be a doublet as well. You could have this relation with doublet, with not doublet, triplets. But to keep it simple, we are going to talk about singlets, and they can change with these omega as omega squared and 1, and that generates 3 different models. So in the first one that we call here F, the coupling between the scalar, the singlets, and mu tau or EE. So you would have this charge flavor violation allowed with mu and taus. If you choose the second model, then we're going to write the coupling as G, and this would allow this E tau decay, the E tau interaction. And the third one with H would give us the E mu and tau tau. Okay.
This K has the charge, the T charge as well.
It does, yes, it does. And that you see this omega, it's omega with the T charge. So you choose the T equals 1, 2, and 3, such that we have K proportional to omega squared and 1. So this is choosing T equals 1, 2, and 3. So it does, yeah. Okay, so we have this first paper here the group made in collaboration with Inés Bigar and Hay that shows the constraints of the tau decays at Belle II. So these models would allow very rare tau decays such as tau to E gamma, tau to mu gamma, or +2 leptons. And if we compare with Belle present constraints and Belle II future sensitivity, sorry, they did this, they compared with the present constraints and the future sensitivity. And this is very interesting because Belle II would have a very high luminosity, and the projected sensitivity is also extremely precise. You see a difference of 2 orders of magnitude between the constraints and sensitivity. And you can see that the results, for instance, for the parameter space of F1 and F2, that is the first T equals 1 model. We have here the mass of the doubly charged at 1 and 5 TeVs. And this is constraining these decays of tau to mu plus E minus at present and future sensitivity. Okay, so what we did here is to compare the results for Belle II with the proposal of a new collider µTRISTAN. This collider is proposed at KET in Japan. And they claim that, they say that they already have this ultra cold mu technology from the G-2 at J-Park. So they can use this technology to create a muon beam. So there are two proposals. One is to create a mu plus collider at 2 TeV in the center of mass energy, which would be 1 TeV per beam, with an expected luminosity of 12 inverse femtobarns per year. And the second proposal is to use 1 mu plus beam at TeVs with an E minus beam that they already have at the Tristan experiment that goes from 30 to 50 GeV. So it have this asymmetry in the energy of the two beams. And in this case, the expected luminosity is of 100 inverse femtobarn per year. Well, we listed here all the possible scatterings with the leptons allowed in the lepton triality model. And we see here that there are 5 possible channels for µTRISTAN to probe, and 3 of them would have charged lepton flavor violation. So we calculated each scattering channel. And so this first one is mu plus, that is the first proposal, µTRISTAN, that would produce tau plus E plus. And in this T equals 2 scenario, and here we have plotted the 90% contour levels, 90% confidence level contour, assuming no background. That means 2.44 the number of events. So we calculate the number of events and make the contour where these would be sensitive. Okay, so we have the contours here in these colorful lines for 1, 2, 3, and 4 TeVs in the center of mass energy. And we see here the resonances for this case, which is also an interesting research experimentally. And here we can see also, so sorry I didn't explain you. So this is the coupling G1 times G2 with the mass of the scalar. And here we have bounds for the mass of the scalar at LHC searches and the constraints for Belle that we already have from the previous paper, and the projected sensitivity for Belle II. So you see it's clearly close to our results. However, the Belle full run would be this dashed line. And what we plotted is only 1 year of µTRISTAN. So in 1 year, we can see that it will already be competitive with Belle II results. We have this EFT limit that is pretty much the end of these lines with the higher masses where the curve is linear. And we see here that this is, we can extract this G1 times G2 square root to an order of 0.15. Oh, I forgot what it was. N over LS. I think it was number per luminosity, mass of the scalar per TeV. This one is expected for Belle II, and if we do something similar for the center of mass energy at 2 TeVs at µTRISTAN, we'll have 0.17. So this is the second result for a mu plus E minus, for the mu plus E minus collider proposal. In this case, also it's interesting to show you that we have a more constrained result, because they explain us first the energy is not that high. We would have an energy of 0.3 TeV to 0.7. And also we would need to have a shield around the mu plus beam, because muons, they decay easily, so we'd have radiation coming from them. So this is also constraining a lot these results. Even though we do have some sensitivity of µTRISTAN that is also competitive with Belle II, sorry. So if we compare the results of Belle II and the µTRISTAN, it's easier to see there. Okay. We see here that for the tau decays, our curves would be sensitive at these 0.17, for instance, mass of the scalar per TeV, with the full luminosity of the run of Belle II. And if we compare the results for µTRISTAN, this is actually lower, it's 0.7, so µTRISTAN would be less restringent, and it would have the sensitivity as well. And also this is true in only 1 year of µTRISTAN and not the full program. So they would have a complementarity between the two programs, even though it'd be very interesting to see those results. And µTRISTAN can also probe only G2. So it's also some other research. It would be different from the channels we have measured in Belle, Delphi, and Belle II. And we also have the research for the resonances on the doubly charged scalar. Okay, last part. It's another work we did with the next leading order constraint.
Can I ask a question about the?
Yeah, of course.
I don't know if I zoomed out in times, but I did not quite understand the symmetry, because you were talking about the Z3 that has to have a charge of 3 equals 3, and the tau as a specified charge that is T equals 3, and so it's the mu and the electron. But the channels that appear in this table has different values of 3. So I don't know if.
No, it's not different values of T, sorry. I don't have the T here, okay?
Oh, okay.
These are the processes, for instance, a tau decay scat. So Belle will measure the tau decays. They are E plus E minus colliders, but what they're sensitive to would be the tau decay, where we have the constraints. Delphi was also this E plus E minus collider. We have some bounds to their results. And here we have the sensitivity of the µTRISTAN in mu plus E minus. The F and G's are the couplings here. So the coupling would depend on the T charge. So if T equals 1, 2, or 3, we would have these theories. So if T equals 1, we have this K1 theory, which we describe the coupling as F, and allows us to have a mu tau, a K1 mu tau, or K2 EE. If T equals 2, we have the second theory that would have this coupling G and allows us to have K2, write K1 here, but it's supposed to be K2. K2 to E tau or K2 to mu mu. If T equals 3, then we have the H coupling and K3 going to E mu, K3 going to tau tau. Okay? So there are 3 different theories. And either way, we can use those 3 theories to show the scatterings. Okay? So T equals 1, we have mu E to E tau. T equals 2, we would have mu mu to E to tau E. Mu mu to mu mu. So this is just the resonance search. We don't have the charge flavor violation. And mu E to tau mu. And T equals 3, we only have the scattering, doesn't have the resonance, that is mu E to mu E. Okay? So we did that, and we calculate those constraints where we would have a number of events that is possible to analyze. So this is the statistics. We use this Poisson statistics so we need the n equals 2.4 to have something that is statistically significant. And this gives us those bounds at different center of mass energy, depending on the coupling and the mass of the scalar, okay? And we're comparing that to the prediction of Belle II. Belle II is something that is already running, and µTRISTAN is a proposal of something that can be built in Japan. So we do that for each channel that is possible, okay? And what I'm showing here with those numbers is pretty much this line here. So we have the coupling, we have the mass, and we see we see the rate of the line, right? So this is an EFT limit that we can calculate also. And I'm going to show you here is those lines in the plot, and we can see here the numbers, and they are pretty similar. However, this is the full, I think, 10 years of Belle II combined, the predictions, and the µTRISTAN is only 1 year. So probably this would run for more years, and it would be even more constraints. Okay, and we can also measure a different channel, that is this mu plus, and have a constraint in only G2, coupling G2 that we don't have in the present constraints we know. Can I go to the next leading order? I don't have much time though.
Let's go.
Yeah?
Let's go. I think it's better than what you would do.
Absolutely.
Because he said it.
Okay, in this case, we're assuming that we have a doubly charged scalar. And we're using the potential we did with the lepton triality. So in general, this doubly charged scalar would have this Lagrangian, and we can apply that to the triality scenario I just showed you. And in this case, we would have corrections at one loop for the Z to 2 leptons, Higgs to 2 photons, and Higgs to Z gamma. Questions about this? Do you guys know what one loop is? Yeah, no, the two behind. One loop. No, so these are quantum corrections. If you go to quantum field theory, we have the interaction. The first thing we do is to expand the interaction in a sum of a Dyson series. Do you know perturbation theory? Okay, so you have the perturbations theories. If you take the first part, this is what we call tree-level, and we would have interactions that look like this, right? This Feynman diagram. If you take the second part, then we have quantum corrections, and then we add diagrams like those, okay? You would have a bubble inside or something. That is a quantum correction. So these processes, that is like the Higgs going to 2 gammas, is something we have very well measured in the LHC, for example. And the future colliders proposals, they tend to have a higher luminosity. So they're going to make those measurements with a very high precision. And if you have a quantum correction coming from something beyond the standard model, a new particle, then we probably can measure them through those corrections with a very precise collider. So we have the LHC, we were increasing the energy to see if we could find a heavier particle, okay? And some of the future colliders, like FCC, they would run in actually a lower energy of, for instance, the mass of the Z, with extremely high luminosity, with a lot of events. So we can measure even more precisely those events and see if the quantum corrections shows us a presence of a heavier particle, okay? So K would be a heavier new particle that we never measured, and we want to know what is the effect on those colliders. Can you understand a little? Yeah. So this is the result for the correction of the Z to 2 leptons. So initially we would have this first diagram that is Z to L plus L minus. If we correct at one loop these vertices, we would have diagrams like these 2 triangles where we include the scale, the doubly charged scalar K. There are more diagrams we took into account that are called self-energies, but just showing you those 2 that are more interesting, how they work. So here we have the plot with the results of these corrections compared with the precision for each experiment, okay? So Y dagger and Y, of course I forgot to write it here. Yeah, sorry about that. But Y dagger Y would be the coupling of the Z going to 2 electrons, okay? No, sorry, the coupling is this delta G of Z to 2 electrons, and Y dagger Y would be the Yukawa coupling. Yeah, that's it, sorry. And comparing the delta G, that is the coupling, with the precision of each experiment, we obtain those lines in terms of the mass of the scalar. So if we compare the results from LEP was the collider before LHC, who's not from collider might not remember. So these are existing constraints with LEP that gives us the yellow line, the contour. And the projections of the high luminosity LHC plus ILC running at the mass pole of the Z, that is called giga Z. So they're going to have the luminosity increased at the Z pole, it's called giga Z. In purple, we have the result for CEPC, and red is the FCCEE. So these are all, I believe, E plus, E minus colliders that are proposed to be built in the future. And we see how they would improve this measurement of these possible quantum corrections from the scalar. Okay, can you follow a little? Yeah.
Each line represents the experiment constraint.
Precision.
Okay.
Okay, so we have a table. I can show you later on the paper. We have a table containing the precision of the prediction of precisions of each experiment to each channel. And we compared our calculations of this delta G. So you remember from quantum field theory that this would, when we calculate the coupling, so we would have G equals this G naught 1 plus delta, right?
Yes.
And these we calculate from the loops.
From the loops, okay.
Okay, so this is what we're doing. And we compare this delta with the collider precision directly.
Okay. Okay, so it doesn't include the tree level. It's just the collections itself, themselves. So
Okay.
this Y data.
That comes from, that's the coupling from the UCAL interaction.
Okay.
The thing is that we had to rewrite this paper when there was some disagreements with the reviewer, and we rewrote the paper in the end to something a little more generic, and then apply to the triality sector, because in the first part we just did the triality. So the Y would be actually the F, G, and H. There is a correlation between the F, G, and H.
Okay.
I just forgot to make this correction this slide. Sorry. So this is the result for Z2L plus L minus. We can do something similar for Higgs to 2 photons. Then we would have those two diagrams that would, where you can see where the scalars would correct these couplings. And here we have a plot with the present constraints from the LHC. So our kappa phi is the coupling between the Higgs to 2 photons, the Higgs and the 2 scalars. And we plotted it in terms of the mass of the scalar. And this would give us a constraint with the LHC by comparing this ratio R gamma gamma. And the ratio is the decay width with the standard model plus the beyond standard model divided by the standard model, okay? So we know from Atlas researches that R gamma gamma was measured from 1.088. So this 088 is the difference between, is where we have a precision, and we can, we need to see how much the R deviates from 1. Because if R equals 1, we see that we have only the standard model, okay? So we have this 0.88 plus minus 0.09 that gives us how much we can deviate from the standard model, still preserving the experimental constraints, okay? That's how we obtain this yellow yellow part that allows us to have a new doubly charged scalar.
Sorry, the yellow part, so is the loud part?
It's allowed.
Okay.
And we did a similar plot with the future collider sensitivity. So we have here in orange the high luminosity LHC. In orange is the high luminosity LHC precision with 6, with 6 inverse autobarns of data. In blue, we have future E plus E minus colliders. So we had all of those click C, PC. They were similar. They were a similar value, and we plotted all in blue, with a delta kappa of 1.3%. In green is the integrated FCC program. That means all the runs of EE, EH, and HH. That would give us prediction of delta to 0.29%. However, I must remember that the whole FCC program would take about, 100 years. So it is possible, but it would take a very long time to reach this precision. And these are the results for Z gamma. So it's similar. We calculate the ratio to Z gamma, and we plot here the results for Z gamma at 3, 1.5, and 0.69%. These are, I believe that only FCC HH would reach such a precision. It would be very hard. Plus, we also plotted this R, which is the ratio between Z gamma and gamma gamma. And we see here that gamma gamma is a much more stringent channel. I mean, it would be easier to see, and also the precision is better. So the Higgs to gamma gamma would be more competitive. So in summary, I showed you here the model of lepton triality and how it would avoid the charged lepton flavor violation from mu decays, allowing the tau interactions. And we show you the predictions for Belle II and µTRISTAN, where µTRISTAN would have the mu plus, and mu plus E minus collider. We can do resonance searches at the mu plus, and be sensitive to charged lepton flavor violation channels in both of them. And also showed you the next leading order results from a similar, bit more generic theory that can be applied to lepton triality, from Z2 to leptons, Higgs to gamma gamma, and Z gamma. That is it.
Exactly 1 hour.
I'm so sorry. I told you I talked too much. You should have stopped me. And I was feeling sorry for the two that didn't understand what I was talking about.
So it's something that I think you know, it's because we take our meetings. Usually, this is because they are on vacation.
Okay.
Usually, our meetings are divided in two. First part for the undergrad, which is usually a more basic subject, and the second part, which would be something like you, for the grad students. So usually in the grad students, despite our attempt to make things somewhat elusive, they don't have to be that elusive, because the focus is for us to discuss more in-depth knowledge, and there will be dedicated time in the meeting for them as well.
Okay.
So
Don't feel
don't feel
pressure.
bad about it. it's good for them because they at least can like learn from a small Z. They listen to it enough, so at some point it will like click.
Okay, so does anyone have any other questions, or should we end up things here?
I think my questions would be more specific about the symmetries because they are, I'm not used to these modular symmetries. But I
Yeah.
already found something here.
Can I stop the presentation? Does anyone else have a question?
Yes. Para a apresentação.
Oi?
Para a apresentação.
Ok. Mas eu continuo aqui ou desligo? Ok, thank you very much, everyone. Bye.
Dá um stop no StreamYard também. Você acha navegador?
Aqui.
And stream.